Good afternoon. Today we are going to talk about some of the basic premises by which geometry is built. It's stale stuff, I'm going to warn you. There's a lot of vocabulary here, but if you can just help me and power through it, that will help build a solid foundation for the rest of the year. I am starting us on this page. I am not going to read you every detail that's shown in this table. You can peruse that at your leisure. But I help you identify some of the more important things that are identified here. We're going to start with a term, a picture of it, what its characteristics are, and then the words and symbols that are used to represent that term. Folks, it seems like the words and symbols might not be all that important, but please pay special attention to the notation that we use, because it actually is crazy important and will likely frustrate you throughout the year, because we are a bit of sticklers about it, but it is important. So just keep that in mind. The first term is something I'm sure everybody's familiar with. It's called a point. And a point has no dimension, has no size. It's just a point. We represent it with a capital letter. It's usually represented by a dot. This dot has dimension. It's thick because you couldn't see it if I didn't. You just name the point. There's no special symbols associated with points. Straight lines. Everybody knows what a straight line looks like. And sometimes we call it a straight line. Often it's just a line. Example, we have a line and it's named so many different ways. One of the things that's really important about lines is it only takes 2 points to create a line. And any of the 2 points will help you identify all the other points that are on a line also. So even though we only name 2 of them, that doesn't mean that there can't be an infinite number of points on our line. When we are naming these, we use any 2 points that are on the line. In this particular case, it's FG, and we actually put a line on them, and those on the ends are extremely important, as they tell us that this configuration goes on forever and ever in both directions. So it's infinite. You studied those in linear algebra, so I feel like that's something you should be comfortable with. The order that you name these does not really matter. Sorry, folks, I think we had a little technical difficulty there. As I was saying, the order that you name the points on your line does not matter. So line FG is the exact same line as FE, which is the same line as EG. We can also represent it with a lowercase cursive letter. So that's a different way to see a line written. The most important thing to remember is that any 2 points can create a line, even if the line is not drawn between the 2 points. Because we have 2 points, we could have a straight line. The next construct to talk about is a plane. A plane is 2 dimensions. It goes on forever in all, left, right, up, forward, backwards, however you want to think about it. I think of it as like a piece of paper, or maybe the ceiling, just because it's just a decent representation for my brain. However, paper doesn't go on forever, but it works. It's a way to visualize it. There is no particular symbol for a plane. You can represent it with a cursive letter, and you'll notice that this has a cursive letter R here. Any 3 non-collinear points, and we'll talk about what collinear is in a moment, but any 3 non-collinear points that are not on the same line, can create a plane. So in this particular example, because S and V and P and T are not all 4 on the same line, then I know that those points create this orange plane that you see identified here. Okay, so those are the 3 basic things that in geometry we just assume to be true. We can characterize them, but it doesn't have a strict definition. The rest of the terms we can actually define. Line segment, you're all familiar with this. A line segment has 2 endpoints. It has a starting place, a stopping place. We can measure line segments, and I can name them in either order. To write down what a line segment is, or to identify one, we use two points, the 2 end points for the line, and draw a line above it. Notice that this line segment does not have arrows on the end of it, so that's how we know it's a line set, not a straight line. The next construct is array. Array is an endpoint, and it has another point on the ray that continues in the direction of the line that continues forever. So it has one endpoint, extends infinitely in the other one, only has a starting point, but no stopping point. We always, always, always draw the representation with the endpoint first, and then an arrow on one side. The representation, the line above it, it shows a ray, and notice that there is no arrow above the B because E is the endpoint. The arrow shows it extending in the direction of A forever. So you have to put the endpoint first, left to right. It's kind of weird, you'll get used to it. Opposite rays, this is kind of, you're gonna think this is kind of silly. Opposite rays are two rays that have a common endpoint and extend in opposite directions. So in this example, it's ray CA and ray CB. Now notice when I wrote them, I used the endpoint C first. CA tells me that C is the endpoint. It extends towards A forever. And then the other opposite part of this ray starts at endpoint C and continues towards B forever. Angles. We all know what angles are. Y'all are good with angles. There's a lot of angle work that gets done before you get to geometry. Technically, an angle is created by two rays that share a common endpoint, which is called the vertex. We name it by either using an angle symbol and the vertex. You can put numbers inside the angle, and you can use that number to represent the angle. Or you could use 3 points where C and B are on the sides of your angle, and A is the vertex. Notice the middle letter, when you name it with 3 letters, has to be the vertex. What else do we have besides a sliding paper? Oh, as promised, the definition of collinear. Collinear points are 3 points that lie on the same line. 2 points are always collinear because it only takes 2 points to make a line. The 3 points are called collinear. 4 points could be collinear. So in this example, K, L, and M are all collinear. Because we have collinear, we can also have nonlinear. Non-collinear are points that do not lie on the same line. I wrote as drawn, that's unnecessary. So in this particular case, point N is not collinear with the set of points KLM, but because any 2 points can make a straight line, K and N by themselves are collinear. We also have coplanar. Coplanar are points, lines, segments, rays, all these things that live on the same plane. If you think about this piece of paper as a plane, then every dot of ink on this paper would be coplanar. Right? So any 3 non-collinear points will always be coplanar. And that's the important thing to remember. Any 3 points can make a plane, unless they're collinear. And then lastly, we have non-coplanar. Non-coplanar is a weird concept to think through. So you can have points that are on your line. In this picture, in the up and down plane, the vertical plane N, I noticed that A and C form a line. A, B, and C, and D actually all could be points on that vertical plane, whereas B, C, E, and D lie more on the horizontal plane. Because of that, we could say that A, C, B, which are on plane N, are not coplanar with point E. Another way to represent this, and sorry that we aren't able to do this in person, but another way to represent this is just to take a little card, right? So here I have a card that has a hole already pre-drilled into it. A, B, C, which is this big hole, and D are all collinear points. But if I stick a pencil or a pointer or something through point C, then the end of this particular stick is not coplanar with any of the points that you see drawn. All right, that's Palmer's goofy representation for non-coplanar. Let's see what else we have in store. All right, we're going to continue talking. You may notice that this first lesson that we do in geometry has really no math in it. And so you might be confused and wondering if you're really in a math class. We absolutely will do lots of algebra and we will do lots of math. But today's lesson is just creating the building blocks for that. And so it's mostly just vocabulary. Let's start with postulates. Postulates are things that we assume to be true. We assume that gravity exists. If I drop my pen, it will fall to the ground. Think of that as a postulate. There are a few postulates in geometry that are very important. We don't have particular names for them, but you really want to know these. We've already talked about this one. Through any 2 points, there's exactly one line. It's a fundamental belief we have. Another postulate is that a line contains at least 2 points. Since it takes 2 points to create a line, you have to have at least 2 points. The next postulate says that through any 3 non-collinear points, there can exist only one line. No matter how you lay them out, there's only one line in which any 3 non-collinear points, there exists exactly one. I'm going to correct myself. This should be a plane. There exists only one plane through 3 non-collinear points. You can't have a line if your 3 points are non-collinear. My fault. Apologies, folks. The next postulate says a plane can contain at least 3 non-collinear points. It has to, by definition. The next one says if 2 points lie in a plane, then the line containing them is also in the plane. That seems pretty straightforward. When 2 planes intersect, their intersection forms a line. If I look at my 2 cards, again, when these two planes intersect, you'll notice there's a crease. Think of the crease as a representation of a line. So that's that postulate. And that's it for our postulates. There is another type of construct in geometry called a theorem. Theorems are things that we have to prove. We will prove some theorems in geometry. We do a lot of proofs. A lot of the theorems, however, that we use, we are going to take on faith that someone much smarter than myself has already proven them. Here are some fundamental theorems that we rely on rather heavily in geometry. If 2 lines intersect, they intersect at 1 point. If 2 lines intersect, then exactly 1 plane contains them both. So those are our 2 theorems that we're going to start with. Let's look at an example. I've got a picture here, and I'm just trying to surmise some things that I can figure out from looking at this picture. Be careful when looking at pictures, folks. We don't want to assume things, but we also want to remember that our postulates and theorems allow us to talk about more than what's shown. Okay, but just looking at the picture, I noticed that X and B and Y are non-collinear points that live in the same plane, plane R. So they are coplanar. I noticed that A, B, and C all live on the same line, therefore they are collinear. I noticed that plane R, this gray rectangle that you see, which represents our plane, and the line C intersect at point B. And the reason this is shown with a dotted line here is to show you that this line goes through the plane. It does not live on the plane. And my goofy pencil through the card is a representation of this. So you can't see the part of the pencil that's underneath the plane, even though it's still there. So the way we represent that pictorially on paper is to show it as a dashed line. Ray BC and ray BA are opposite rays. They share a common endpoint and make a straight line. Point C is non-coplanar with plane R. Point C does not live on this plane, nor does point A. There are other things that this picture doesn't show that still exist, however. There is a line, CY, that could be created because any 2 points create a line. I could also create a different plane through point B, Y, and C because any 3 non-collinear points can create a plane. So there's more than just what's shown in this picture that exists. These are the things that we do see. Here's another example. Remembering that we're not going to think about just what's possible, and not what's, we are going to think about what's possible, not just what we see. So if I look at this one, it says our points S, which is down here in the corner, point O up in the top corner, and point M coplanar. Well, as drawn, absolutely not. But if you think of this as a block of cheese, perhaps, you could definitely slice this cheese along the diagonal, and then O, S, and M would be on the same plane. If I'm looking at how many planes are shown, I can count 6. Think of a box of tissue, if you will. There's a front and a back, a left and a right, and a top and a bottom. Your box of cereal that you delve into in the morning is also a good example of this picture. Okay, let's look at some more examples. Again, we're using our box of tissue or a box of cereal as our representation for this picture. Example C, 2C, is asking us to name the intersection of plane LON, which I would call the top, and plane PQM, which would be the front. And two planes will always intersect at a line. That was one of our postulates. And in this case, that line happens to be LM. And if I wanted to use my little cards, I would say, here's the front. And here, LON, here's the top. And these two intersect at a line. This one says, name the intersection of plane MQR, which is the right-hand side. I'm not great with left and right. MQR is the right-hand side, and line ON, which is this back line. So if I use my goofy representation, here is the right-hand side. And then if I use a line, I'll notice that they really are only going to touch at one spot. A plane and a line intersect at a point. So I am naming the intersection, and that is point N. Do S and M determine a line? S and M. So if you're just looking at the picture, you're like, no, there's no line between them. But remember, through any 2 points, there is exactly one line. So yes, they do determine a line. How many lines are there through N and Q? That would be just one, because through any 2 points, there is only one line. How many planes are there through points S, T, and R? And you'll notice S, T, and R are collinear. They're all on the same line. And the answer to this one is kind of weird. The answer is infinite. There are an infinite number of lines that go through there are an infinite number of planes that go through the points S, T, and R. A real world example of this, although you'll have to stretch because we know lines have no dimension, but if you think about a spiral notebook, you could get an infinite number of pages that go around the metal spiral on the edge. Right? So the spiral, the metal part would represent the line, and the pieces of paper would represent all the different planes that intersect with that line. Name the intersection of line PS and line OS. PS and OS. That would be this line and this one. And the answer is S. Two lines intersect at exactly 1 point. All right, last one. Nope, next to the last one. How many planes contain line LO, which is this back line, and line OS? How many planes contain those two segments? Only one. Through any 3 non-collinear points, there can be only one plane. Oh gosh, there's lots more. Sorry about that, folks. J, is line OM in plane LMN? So if I'm going to look for line OM. It's not drawn, but it could be because 2 points make a line. Is it in the plane LMN, which is sort of this top piece? And yes, it is. If 2 points lie in a plane, then the line containing those 2 points is also in the plane. move that up so you can actually see the answer, and the answer is yes. So you'll notice to answer almost all of these, we used postulates, theorems, and definitions. Example 3 is yet another picture. Example 3 is asking us to name 3 points that determine plane J, which would be this one, right? Ooh, I'm going to go that way. 3 points that determine plane J. And there are actually more than 3. As drawn, I see W, V, and Z. Those are easy to see. Remember, a plane extends upward and this way in all directions. Plane J does. It extends infinitely. So you could argue that plane U, or point U, is also in plane J. But to make our brains comfortable, I just wrote down V, W, and Z. Name the intersection of the 2 planes, J and K. Well, we know that's going to be a line because 2 planes always intersect at a line. And we can note this line in lots of different ways. All of these notations represent the same line. Notice I used 2 points that lived on the line, and I drew a bar above them that has arrows on both ends. Name a set of collinear points and a set of non-collinear points. Well, all the points that we identified up here would be collinear. They live on a line. So my linear points would be U and W. Non-collinear points, as shown, would be V, W, and Z, or V, W, and Y. If I take off any one of these, the points become collinear, but because there's 3 of them, they are non-linear. And lastly, it says, name the set of points other than those in part A that are coplanar. And so coplanar points I said were U, X, and Y. U and X and Y, 3 non-collinear points form a plane, and that's where I came up with that one. Folks, that's it for our first day of geometry, or the first lesson. Day is sort of an ambiguous term. That is our first lesson. I hope you enjoyed it, and I promise we'll do some math with numbers in our next